Alright, we're starting part 2 of our video on working on the Verdin bell tower amplifier system. And what I have here, I'll show it to you, is a model P155 made by McIntosh Laboratories preamp. And you can see it's very simple. It has a power cord which is powered by the DC in that P237 amplifier. It has a single mono output. It has a tape and phono input that, if you look, are just physically tied together. And it has a separate microphone input. And if you go to the front for the controls, all you have is normal and mic switch over, treble, bass, and a volume. And that's it. It's a very simple chassis. And you can see it picks off that 100 and some volts. So if you look on this amp here, you really can't see. If you look at the power supply, you see down here you have this 90 volt and 80 volts. On the P237, it picks up this off and goes to a connector that will connect to this, and that provides the power, the DC power for this. And you got it. Once it gets out here, they run it through a dropping resistor, a little tiny one. This is very low current. And then through another series of dropping resistors with a capacitor filter. It's a very simple circuit, but it does have, if you notice, 1, 2, 3, 4, 5, 6 transistors. And this is mono. Plus it has a couplet or couplet, however you want to pronounce it, which is basically just a network of capacitors and resistors. And this basically is your bass and treble tone control circuit all in one. Now, here's where we're at with it right now. And that is, I've just done some preliminary testing on it, and it does have a little bit of a noise. I don't even know if I'd call it an oscillation, but it does have a noise to it. And that noise seems to be more prevalent when you work the bass control. If you turn it up a little bit, it starts to get worse. Now that could be that just because the noise is in that frequency spectrum, that the bass control just filters it out when you turn the bass down. Or it could be something in this network is bad. It does look like this first transistor, which is, this is the one where it comes in at. From looking at it on the scope, I'm thinking that these transistors are a little bit noisy, which doesn't surprise me. They're all the same. They're all NPNs basic. I think they're similar to a 2N2222, all of them. But the signal will go in clean and it'll come out really highly amplified. This amp is super, super high gain. When I say that, the minimum signal my signal generator can put out is 1 millivolt RMS. That's it, which is tiny. If I put 1 millivolt into the tape input on this, I can drive that amp into clipping very easily by turning the volume up on this. So you can imagine how much gain this thing has. So it is very susceptible to noise. So I don't know how much I'm going to be able to totally eliminate the noise, but what I can tell you is I'm going to do my best to get it as much as possible. There's really not a whole lot in here other than if some of these carbon resistors have a little bit of noise to them. These two electrolytics may be bad. I don't know, I doubt it, but they may be. But other than that, there's really not a whole lot. So anyhow, as we go on to this more, I'll get into it more. But really what I want to talk about a little bit for this video is the uniqueness of these older McIntosh Solid State Amplifiers. They use some very unique things that you don't normally see in other amplifiers. Now, my first disclaimer is that I'm not going to sit here and tell you this is the best or that is the best, because that's just not true. Nothing is the best and nothing is the worst, because each individual person has a different preference for how things should sound, and each individual person has different hearing. I mean, case in point, if you take me, for example, when I was in my 20s, 30s, whatever, I could hear above the spectrum. I could hear clear up over 20 kilohertz. I could hear it plain and clear as day. Today, if I can hear over 12 or 14 kilohertz, I'm considering myself lucky. That's about, because as you age, your ears change. So what sounds good to me may not sound good to someone else. So that's my first disclaimer. Now, I got that out of the way. So, but what I am going to say is some of my opinion and just some of the observations I've made by working on this amp. The reason I have the schematic out is, if you look, this is a transistorized amplifier. So you have basically a driver circuit, and then you have your quad outputs, and they're calling these a Class B output section, okay, instead of Class AB, and which has to do with the biasing. But the unique part I want to focus in on is right here. When we come out of here, we go into what almost looks like a vacuum tube output transformer. And if you look on the MC100 and 2100, you have a 16 ohm, 8 ohm, and 4 ohm tap, just like you would on a tube amplifier. On the P237, the difference is it has a 16 ohm tap, and then it has a 70 volt line tap. Now for any of you, excuse me, alright, I'm back. So anyhow, the P237 actually has a 16 ohm tap and a 70 volt line tap. And what is a 70 volt line? Now most of you may know that, but some of you who are new to this, 70 volt line is called like a distribution line. And what it does is it takes this lower impedance output of your transistor and it boosts it up to a higher voltage level at lower current so that it can travel across long distances, just like your power system, like the electricity that powers your house. On top of the telephone poles, your utility lines, you have many thousands of volts. Then it goes through those round transformers up on the pole, and it steps it back down once it gets where it's going to 240 volts, which comes into your house. And we're doing that with sound with a 70 volt line transformer. So on the P237, this transformer, the windings are a little bit different. It has more turns on it that boosts that voltage up, and then once you go across your long distance line, let's say it's a PA system, so you're distributing the sound throughout maybe a large building or a store or something, and then at each point you want to put a speaker, you would put a step down transformer, which is a small little transformer, and it's going to take that 70 volt line and step it back down to 4 or 8 ohms, and then go to a small speaker, and you can put many of those on there. Now here's how it works. If you have a 100 watt amplifier and you step it up to 70 volts, you can have multiple low wattage small speaker transformers. So you could have maybe 10 speakers running at 10 watts each, or 20 speakers running at 5 watts each maximum. So these output transformers, these matching transformers, not only do they step the voltage down, but they also can step it down to a wattage limit. So you can have 1 watt, 5 watt, 10 watt, or whatever, okay, depending on the design of the transformer. So basically it's designed to have, instead of one loudspeaker, you have speakers spread out throughout a large area at lower volumes to distribute the sound. Okay, so that's what that is. And of course, being that Verdin bell tower being a commercial device, a lot of times the bell tower speaker is very far away on top of the steeple or wherever you're putting it outside the building, and you're going to take this and step it up so that there's no line loss of the speaker leads that are going 150, 200, 300 feet wherever they go. And then you have a matching transformer on the bell speaker that's up in the tower, and you step it back down to speaker level, which would be 8 ohms or whatever. Okay, so it has that, and then it also has a 16 ohm tap for old-fashioned 16 ohm speakers, which unfortunately we don't use those anymore. So the P237, in order to use it with a regular speaker, we may need to change the transformer or change our speaker or do something else. Now, if you look at this on the schematic, one thing that we notice, and I'll zoom in for you a little bit, is right here, this comes out of the transformer, or out of the transistors. So this would normally be the output that would go directly to your speaker. But what they're doing at McIntosh is they're running this down into the bottom tap of an auto transformer. And again, they call this, for marketing purposes, they call it the Autoformer. It was that second big transformer that you saw on that amp. Okay, the first one was the power, the other one was this. And then what it's doing is, you're going in at a low impedance, which would be like 2 ohms or something, and then you're stepping it up for a 4 ohm load, 8 ohm load, and 16 ohm load in this instance. Okay? Now, why on earth would you do that? Because we know that on a normal amplifier, they just come straight out of here, right here. And let's back you up a little bit so we can see better. They bring you straight out of here, and they just go straight out to the speaker normally, right? And when you do that, when they rate an amplifier, they will pick a standard impedance speaker. So for instance, they would say, this thing puts out 100 watts at 8 ohms. But that also may say, and a lot of them do, at 4 ohms, if you connect this to a 4 ohm speaker, it will deliver 160 or 180 watts, way more than it does at 8 ohms. Now, why is that? What causes that? And the difference is, McIntosh says, it's 100 watts and I don't care what you hook up to it. Anything that's a 4 ohm, 8 ohm, or 16, we got it covered. It's always going to be 100 watts maximum. That's it. So, why would I want to do that? I'm cutting my power down then, you're telling me. I mean, if I can get 180 watts by hooking up a 4 ohm speaker to a regular amp, why would I want to buy this thing and only get half of that if I hook up my 4 ohm speaker? Let's try to explain some of this. So, here's what we've got. I'm going to draw you a block diagram on TonyCAD. Okay, so this represents our amp. This represents our speaker. Okay, and if you look, what I drew in these boxes is simply 2 resistors going to ground from a voltage source. Now, this is typically a very low DC resistance. Low resistance. All right. So this is usually a low resistance. I'm going to have to get used to my schematics. And this is usually going to have a higher resistance. Now I'm going to put a little arrow because it's not real high resistance, but it's higher than this one. Okay? But more importantly, it has what we call reactance. Okay? What does that mean? Or impedance. What is impedance? Okay? Impedance just means resistance that changes, okay, that changes with frequency, right? Resistance that changes with frequency, delta. That delta means change, right? So resistance that changes with frequency. Now, that's why I drew this like a pot, like a potentiometer, a variable resistor. Now, what are these resistances? What makes it happen? So for the amplifier, let's go back to our McIntosh schematic here. You have the transistors themselves, right? Okay. You have resistors for current limiting, right? We have all the other circuitry in here that's involved, right? All of that kind of adds up to a certain DC resistance, right? These all have DC resistance, but they also have, like a semiconductor can change how it looks as a resistor to a power source based on how you bias it, correct? So, but for the most part, when this is turned all the way on, okay, full power, fully biased on, this just has a small drop across it. This has very small, this is less than 1 ohm. I mean, we're talking 0.3 ohms, okay? And these current limiting resistors are here, just that if something overloads here, this guy takes the hit instead of this guy and protects your transistors from peaks, okay? Because this is such a low impedance circuit, you have to have something in there, or if a transient or a spike of sound comes through there, it could actually exceed the limit of the semiconductor and damage it. In this case, though, that would be carried off into the resistor as heat. So it's kind of, that's why it's called current limiting. But anyhow, it has a relatively low resistance. And so as a result, this is considered a low resistance. Up here, let's say we have an 8 ohm speaker. Okay, so this resistance is typically, all right, typically less than 1 ohm. Okay, so I should draw it this way then, right? Less than. The alligator eats the bigger thing, right? Okay. So resistance is less than 1 ohm. Okay. So in here, our resistance is 8 ohms if it's an 8 ohm speaker. An 8 ohm speaker just means on average it will present an 8 ohm load, but that can change depending on the frequency. Remember, it's impedance, it's not DC resistance. But it also has DC resistance. So like if you look at your voice coil, okay, so you have your voice coil, you have your crossover, and you have your speaker wire. And then you have reactance, okay, which could be mostly inductive, but also some capacitive to a degree. And those are what change our resistance based on frequency, because basically a voice coil is a coil of wire around a magnet, right? So this is an inductor. So this can go up above 8 ohms, even higher. It can be 10, 15 ohms, and it can go lower too. It can drop, down to 4 ohms or so, depending on what frequency. As you change frequency, and depending on our crossover and all these things involved, it can be all kind of different resistances. However, for the most part, it's larger than this. Now, if that's the case, so we take that all back out and we simplify it even more, all you have is a voltage divider. Okay? And this is going to change with frequency. Now, if this is low resistance relative to this, and I vary this, what do I have here? I have a voltage divider. Okay? So what's going to happen when I put a signal on here, and I start varying this, putting a frequency on here, okay, an AC signal, what's going to happen is this resistor here is going to be higher than this. So first of all, this is going to get a lower voltage, and this is going to have a higher voltage, proportionate to one another, okay? This ratio, lower to higher, is going to change with frequency. And because of that, current, right, in a series circuit, okay, this is old-fashioned stuff, Kirchhoff and Thevenin, basically means that the current is going to be the same in these all the time. It's just the voltage is going to vary, how we split it up. Okay, so this is not a current divider. Current will be constant through the whole thing. Now we can use basic Ohm's law, and we can figure out, right, that if we want to look at the power going into these, okay, P equals IV, right? Or we can use V squared divided by R, right? Or we could use, what is it, the square root of R over I, or I over R, I forget. Anyways, we can just see how we can calculate the power. Now, if I've got 100 watts of power, because we're talking about amplifiers, and my current is constant, and my voltage is dividing here, the trick is I want all of the 100 watts that's up here in a perfect world to be able to go down to my speaker load, because this is what's turning the power into sound, not this. All this is doing is delivering it to here. All right? So if I change this resistance ridiculously, then, you know, if this drops way down, then more of the power is going to get eaten up in here and less here. Conversely, if I raise this way up, this will eat up a whole lot of power, and this won't, and the overall resistance will go up between the two. Current will drop. Okay? All kind of crazy things happen. You see how everything reacts with one another? It's literally a moving target. Now, here's the thing. What if we can keep this low or into a reasonable level based on the load that I'm putting on it, so that I don't overload this? Now remember, the more I have to deliver to this load down here, my current is still going to be the same. This guy here is going to have to dissipate the same amount of current as this guy. Alright, I hope I'm not confusing everybody. If I put a low, like a 4 ohm load, on right here, not on this transformer, I take the transformer away, I just go straight into here and put a 4 ohm load, and I go straight into here and put an 8 ohm load, my current is going to change through here, because my total resistance is going to change. Okay, because the total circuit resistance is these two resistors added together. Alright. What that's going to do is that is going to make this dissipate more current. It's going to heat up these transistors more. Okay, and anytime you create heat, heat is also part of our absorption. As this converts electrical energy into heat energy, part of my voltage up here is being lost in this heat. So the lower I go in impedance on my speaker, the more demand current-wise I'm going to put on this, and as I dissipate more current through my circuit over here, I am also going to convert more of that current into heat and lose energy. Okay, so it's hard on the semiconductors, and you're also getting some losses. Okay, so even though an amp may be able to handle the 4 ohm versus the 8 ohm, it's harder on the amplifier. Chances are you're probably going to run the risk of getting more distortion, okay, possibly, by running this at a higher temperature. So it's overall not a balanced circuit. However, this is where McIntosh comes in, and again, I'm not selling or talking up or talking down this. I'm just where they're coming from on this. They eliminate that. This is going to see the same apparent load regardless of what speaker I put on here, because this transformer is just going to shuffle the deck furniture around on the Titanic a little bit. Okay, it's going to actually just change exchange some voltage for some current while keeping the overall wattage the same and keeping the apparent voltage divider the same. By not changing this apparent resistance, I'm keeping a more consistent load on my amplifier. That's what we're trying to do here. But we're still delivering the same amount of energy to the speaker. It's just we're matching the impedance better to the amp. So we're getting less heat, so we're getting more efficiency, and technically a clearer sound. Now, here's the thing. I've heard arguments that, this transformer could color the sound. Okay? And again, that is something that it just depends on what your definition of that is. At different frequencies, this is an inductor. It's a coil. So it can possibly suppress some frequencies more than others. But if it was properly wound and the impedance of this part here is properly matched to the impedance that this circuit was designed at, okay, the load that this was designed to work its best at, technically that shouldn't change. So here's in a nutshell. An amplifier, okay, it's just a power supply for a speaker. So it basically has an output, right? So here's your signal. And we know our speaker has impedance. And we know that as the frequency changes, so does the resistance, or the apparent resistance, being reflected back to the amp. In a perfect world, this speaker is going to minimize, okay, with all of its crossovers and different, things you put in there, right? All the different stuff we put, it's going to present a relatively level, as the frequency changes. Okay, so this would be frequency this way, and this would be impedance this way. Okay, so as the frequency across the different frequency spectrum from 20 hertz to 20 kilohertz, the impedance should, in a perfect world, stay very stable. All right, this isn't a perfect world. Now, why do we care? Well, an amplifier has an amplification factor, right? So, for instance, if I have this set up that 1 volt in gives you 10 volts out, the amplification factor is 10 to 1. Okay? Now, here's the thing. In a perfect amplifier, if I put 1 volt at 1 kilohertz, right, I should get 10 volts at 1 kilohertz. And I might. But what happens when I go to 20 hertz? This is going to change. This is going to change. Maybe I'll get 12 volts. Maybe I'll get 11 volts. Maybe I'll get 9 volts. Depends on what this speaker does and what this impedance changes to. Same thing when I'm at 10 kilohertz. If I put 1 volt peak to peak, or RMS, however you want to measure it, I still should get 10. Because the amplifier should not change the signal. It should only increase the amplitude of the signal by a factor of 10. So a perfect amplifier would not care what frequency you're using. It will always put out the same exact amplitude, 10 times, however much that factor is, regardless of what frequency you're at. And what you're going to find out is most amplifiers, these solid state ones that don't have this, can do a pretty good job of that, but may not always do a perfect job of that. And if they do a perfect job of that with an 8 ohm speaker, they probably won't do that with a 4 ohm or a 16 ohm speaker load. So if you have a speaker that's not, do you ever hear people talk about, I don't like the way that Pioneer or that Kenwood or that Krell or the whatever sounds with this particular name brand of speaker. But I like, man, when you put this speaker on this amp, it sounds great. Well, what they're telling you is that they've found the secret sauce. They found a speaker that matches linearly with that amplifier. And when you put those two together, it does this. You get a perfect or close to perfect output. When we have this transformer, we are more closely ensuring that regardless of your speaker, you're still going to get a linear output, amplification factor at all frequencies. So in theory, in my mind, and again I could be totally wrong, when we use this autoformer as McIntosh does, we are ensuring that we are not changing or coloring the sound, but we are reproducing it very accurately. Now some people, again, their ears say, I like hearing the amplifiers that have a little bit higher boost at, when you hear about speakers sound good in the bass range, this amp's got a lot of bass. Well, really, it's not that it has a lot of bass or has a lot of treble, it's that the amplification factor at that low frequency is a little bit higher than it is at the higher frequencies. And it's probably because of the load impedance of the amp versus the load that you're putting it on, the speaker that you're putting onto it. Okay? So it gives you the sense that that amp has a lot of bass. Watts is watts. But how you distribute them or how you amplify and use them at different frequencies affects the sound. So it's a matter of opinion whether this colors the sound or doesn't. Okay, in my opinion, again, this is opinions. Everybody has a different, we could talk about this for months and, and get agreements and disagreements. But this is exactly what I'm talking about. So this is what's unique about this. If I put the proper speaker on this transformer, I'm going to probably have, a pretty linear across the board amplification factor. And that's what I found out with that P237. You know, I put a 16 ohm load on the 16 ohm tap of that amp, and it pretty much, it just didn't really care what frequency I put in it. It was always, if I set that little trimmer pot, you know, the gain pot at the front end, if I set it to a ratio of 1 to 10, it pretty much hung in there no matter what input frequency I put, if it was always giving me that same ratio. So it was a very flat, pure reproduction amplifier. So in my opinion, this was a really brilliant idea on McIntosh's part. Now, can I get an amp without this, or can I eliminate this on this McIntosh and hook a speaker right on here? You bet you. And I can probably find speakers that would sound wonderful without this. Okay, but what the genius behind this is, and the theory behind this is, I have a whole bunch of different speakers that I can use with this that should all perform very similarly because they can be properly matched to the output. I hope I didn't confuse you guys more on this. I hope I kind of explained it. Again, I tried to not get too technical, but just give you an idea of the theory behind why they do what they do on this and why this autoformer is used. Alright, so I don't know if I confused you more than I understand, the thumbs down. If I at least helped you understand a little bit about why McIntosh did, and they talk about the McIntosh Sound, and they talk about that, you know, their old solid state amps have a very warm sound like a tube. Well, that's why. Tube amps, by their nature, have a matching transformer, and they have output taps, and you can match them. And you also realize very quickly, if you hook an 8 ohm speaker to the 4 ohm tap, bad things happen. Also, even especially in the amps that aren't as well designed, really bad things can happen. You could damage the tubes and all kinds of things. So you really get to see on the tube amps how important impedance matching is, whereas these transistor amps are forgiving. They don't care, they just produce more heat, they give off on the heat sink, the overall power transfer to the speaker changes, but other than that, you know, it'll work. So you can get away with a lot more on solid state than you can with tubes. So I hope that explains a few things. It's very interesting to me. I found it fascinating working with this P237, and I learned a lot. I've really never worked on an old McIntosh solid state amp before. This was my first one, and this is the first time I've experienced this autoformer firsthand, and it was a real learning experience. I just thought I'd share that with y'all, and hope you find it as interesting as I did. Alright, you guys have a wonderful weekend, and the next video we're going to be coming back to this little preamp. Hopefully I'll have it cleaned up and working as well as I can get it. And then we're going to do amp number 2, and I'm not going to get real detailed on that because you saw on the first one what all I went through. I'll just go over it, and I'll give you a final little video clip of running the whole thing together, and maybe we'll go on location when we install it back into the bell tower and see how it works. Alright, have a great weekend, guys, and thank you all for watching, and more to come.